Yeah.
The hand might be close to half of all the engineering in Optimus. From an electromechanical standpoint, the hand is probably roughly half of the engineering.
But so much of the intelligence of humans goes into what we do with our hands.
Yeah.
Like the manipulation of the world, manipulation of objects in the world, intelligent, safe manipulation of objects in the world. Yeah.
Yeah. I mean, you start really thinking about your hand and how it works.
I do all the time.
The sensory and control homunculus is we have like humongous hands.
Yeah.
So, I mean, like your hands, the actuators, the muscles of your hand are almost overwhelmingly in your forearm.
Mm-hmm.
So your forearm has the muscles that actually control your hand. There's a few small muscles in the hand itself, but your hand is really like a skeleton meat puppet, and with cables so the muscles that control your fingers are in your forearm, and they go through the carpal tunnel, which is that you've got a little collection of bones and a tiny tunnel that these cables, the tendons, go through, and those tendons are mostly what move your hands.
And something like those tendons has to be re-engineered into the Optimus in order to do all that kind of stuff.
Yeah, so like the current Optimus, we tried putting the actuators in the hand itself, but then you sort of end up having these like
giant hands.
Yeah, giant hands that look weird.
Yeah,
and then they don't actually have enough degrees of freedom and or enough strength. Mm-hmm. So then you realize, oh, okay, that's why you got to put the actuators in the forearm, and just like a human, you got to run cables through a narrow tunnel to operate the fingers. And then there's also a reason for not having all the fingers the same length. So it wouldn't be expensive from an energy or evolutionary standpoint to have all your fingers be the same length. So why aren't they the same length?
Yeah, why not?
Because it's actually better to have different lengths. Your dexterity is better if you've got fingers of different length. There are more things you can do, and your dexterity is actually better if your fingers are of different length. Like there's a reason we've got a little finger. Like why not have a little finger that's bigger?
Yeah,
because it allows you to do it helps you with fine motor skills.
This little finger helps?
It does. If you lost your little finger, you'd have noticeably less dexterity.
So as you're figuring out this problem, you have to also figure out a way to do it so you can mass manufacture it. So it's to be as simple as possible.
It's actually going to be quite complicated. The as possible part it's quite a high bar. If you want to have a humanoid robot that can do things that a human can do, it's a very high bar. So our new arm has 22 degrees of freedom instead of 11, and has the actuators in the forearm. And these all the actuators are designed from scratch. From physics first principles. The sensors are all designed from scratch, and we'll continue to put a tremendous amount of engineering effort into improving the hand. Like the hand, by hand I mean like the entire forearm from elbow forward. Mm-hmm. Is really the hand. So that's incredibly difficult engineering, actually. and so the simplest possible version of a humanoid robot that can do even most, perhaps not all, of what a human can do is actually still very complicated. It's not simple. It's very difficult.
Can you just speak to what it takes for a great engineering team? For you, what I saw in Memphis, the supercomputer cluster, is just this intense drive towards simplifying the process, understanding the process, constantly improving it, constantly iterating it.
Well, it's easy to say simplify, and it's very difficult to do it.